Hi, I'm Ryan Baker, and this is Big Day in Education. In today's video, we're going to continue our discussion of knowledge inference, talking about modifying the assumptions of Bayesian knowledge tracing. Friendly warning, this lecture is going to get mathematically intense by the end. You officially have my permission, as if that actually mattered, to stop this lecture midway. So, as we've talked about already, BKT has strong assumptions, and one of the key assumptions is that parameters vary by skill, but they're constant for all other factors. What happens if we remove this assumption?
So if we remove any of those assumptions, we get different kinds of algorithms that can be used for different purposes, like algorithms for conditionalizing help or learning, algorithms for contextual guess and slip, moment-by-moment learning models, and algorithms that can model the transfer between skills.
Let's talk first about Beck's help model. In this model, help use is not treated as direct evidence of not knowing the skill, unlike classical BKT, but instead it's used to choose between parameters. This model makes two variants of each parameter, one of them assuming help was requested, and one of them assuming that help was not requested. This model otherwise looks just like BKT. It's just that at every single parameter, there's two variants of it. A given help, a given H, and a given not help, given not H. This gives us 8 parameters per skill, the 4 classical parameters times 2. It's fit using expectation maximization, because it takes too long to fit using brute force. Brute force works when we've got an n to the 4th problem, but it doesn't work so well for an n to the 8th problem. Now, in Beck's original paper, he found that there were fairly different parameter values for guess and for slip based on whether or not the person asked for help or not.
Now it's worth noting that this model didn't actually lead to better prediction of student performance, but it was useful for understanding the effects of help. And one of the things about BKT that's noteworthy is that a lot of the modern extensions of BKT actually aren't about fitting the data better. It's funny because the knowledge modeling community in general, the researchers working on it, so many of them are focused on getting like 0.002 better prediction. But a lot of the things that BKT can do for you have to do not with getting slightly better prediction of next problem correctness, but of being able to infer other things. In this case, the effects of help. In related work, Iyad Salomon and his colleagues actually used a variant on BKT to study the effectiveness of videos by looking at differences in PFT by video. What they did was they applied BKT to a learning system with both videos and problem solving. If a student got a wrong answer, they were given a video. And Salomon and his colleagues let PFT vary based on which video the student got, and used this to determine which videos were more or less effective. The second modification of assumptions of BKT that we'll discuss is contextual guess and slip.
In this model, we have the exact same L0, T, G, and S, but the G and S aren't actually parameters fit per skill, they're models. The big idea is why one parameter for slip for all situations, for each skill, when we can have a different prediction for slip for each situation, across all skills. So in other words, P of S varies according to context. For example, perhaps very quick actions are more likely to be slips. Or perhaps errors on actions which you've gotten right several times in a row are more likely to be slips. Guess and slip are therefore fit using contextual models across all skills. And in this case, the parameters per skill are 2 plus the model size of P of S divided by the number of skills, plus the guess model size divided by skills. This ends up amortizing to a good bit less than 4 parameters per skill. So how are these models developed? We take an existing skill model, we label a set of actions with the probability that each action is a guess or a slip using data about the future. We're going to use the data about the future, but we're not actually going to use it in the running model. We're just going to use it to build the model. We use these labels to machine learn models that can predict the probability that an action is a guess or slip without using data about the future. And then we use these machine learn models to compute the probability that an action is a guess or slip in real-time knowledge tracing. So again, we're using the future to build the models, but we're not using the future to actually run the models. So more specifically, we label a set of actions with the probability that each action is a guess or slip using data about the future. We predict whether an action at time n is a guess or slip using data about the actions at time n plus 1 and n plus 2. The intuition is that if action n is right, and actions n plus 1 and n plus 2 were also right, it's probabilistically unlikely that action n was a guess, because the probability that you'd get 3 things right in a row by guessing is just really infinitesimal. And similarly, if actions n plus 1 and n plus 2 were wrong, it becomes more likely that action n was a guess. I'll give an example of this math in a few minutes. Having gotten these labels, we then use them to machine learn models that can predict the probability that an action is a guess or slip. We take features distilled from logs of student interactions with the tutor software that broadly capture behavior indicative of learning. In our original work, Baker, Corbin, and Levin 2008, which is starting to feel like ancient history, we selected these from the same set of initial features previously used in detectors of gaming a system and off-task behavior. In our first work, we used linear regression. Again, by the time we get to the next lecture, we're going to get way past this. But in our first work, we used linear regression, which turned out in this early work to do better on cross-validation than fancier algorithms. One guess model, one slip model. And then, having these probabilities, we just plug the estimates, the numbers, into Bayesian knowledge tracing. Exact same formulas as before. We're just substituting a contextual prediction about guessing and slipping for the prediction for each skill. How did the model do? Well, the effect on future prediction was quite inconsistent. It was much better on cognitive tutors for middle school algebra and geometry, but it was much worse on the cognitive tutor for genetics and assessments. But as it turns out, even though it's not a very good substitute for Bayesian knowledge tracing, this model produces something which is predictive of longer-term outcomes, each student's average contextual probability of slip. The average contextual probability of slip predicts post-test. So it predicts how students are able to transfer their knowledge out of the online learning system. It predicts shallow learners, people who will do well on a test of what they learned from the system, but not be able to transfer their knowledge to new contexts. It predicts college attendance several years later. In San Pedro et al. 2013, she was able to show that average contextual probability of slip for middle school students across the course of the year was associated with lower probability of attending college several years later, once you control for student knowledge. And she was also able to find that it was predictive of STEM major several years later. So, does a student major in a math or science related career? Higher average probability of slip in middle school makes it less likely that you're going to major in science or math when you get to college several years later, once you control for student knowledge. So this is some pretty, to me, interesting uses of this model that was beyond its initial idea. So when we think about what this probability of slip means, this kind of metric that we took out of Bayesian knowledge tracing but we're kind of now using for a different purpose, what does it mean? Well, there's two possible interpretations. The first, from San Pedro, Rodrigo, and Baker 2011, was carelessness. These contextual slips are indicating the student wasn't trying very hard and that's why they got it wrong. They were careless. We thought about this because it maps very clearly to the theory of carelessness in Clements. Theoreticians about carelessness have said that carelessness is making mistakes on things you know. That's what contextual PFS kind of means in some ways. But there's a second possibility, which is shallow learning. Perhaps the student's knowledge is imperfect, and so it works on some problems and not others, and that makes it appear that the student is slipping. We don't necessarily have a clear answer for which of these it is at the moment.
Now, another way of contextualizing guess and slip is seen in KTIDEM by Pardos and Heffernan, where rather than having a single P of G and P of S for each skill, each item has its own P of G and P of S. So whereas contextual guess and slip tries to get a very specific, this moment estimate of guess and slip, KTIDEM is instead just saying each item is going to have its own P of G and P of S in general. Going beyond that, LFKT, no relation to LKT or LFT, by Kaja and his colleagues said, what if rather than having a single P of G and P of S for each skill, we instead adjust guess and slip contextually based on skill and item and student. And for student, we're going to do past performance on other skills. Concurrently, Gonzalez-Brenes and his colleagues developed a model called FAST plus item, which substituted logistic regression equations for all 4 parameters of Bayesian knowledge tracing, not just guess and slip like in the contextual guess and slip approach, but also T and L0 with coefficients for each skill and coefficients for each item. And they found that this led to better prediction of student correctness than traditional BKT or PFA, a little more stably than contextual guess and slip did. We'll now continue by discussing a third way to modify the assumptions of BKT, which is moment-by-moment learning.
The moment-by-moment learning model, as published, takes Bayesian knowledge tracing, and it doesn't actually try to substitute any of the 4 parameters. It just adds a variant parameter for P of t, the probability you just learned. That's not quite the same as P of t. P of t is the chance you're going to learn if you didn't know it already. P of j is the probability you just learned. Or in other words, it's the probability that you didn't know it and then you learned it. Not quite the same thing, although it's quite related. Now when I say P of j is distinct from P of t, actually they can have values that are quite different. Take, for example, the difference between a probability of t of 0.6 in the context where you have an initial probability of knowing it of 0.1 or 0.96. If you had a 10% chance of knowing it and you have a 60% chance of learning it if you didn't know it, the probability you just learned is 54%. That's learning. But if your probability of knowing it to begin with was 96% and you had a 60% chance of learning it, you only have a 2% chance that you just learned it. That's not very much learning. P of j is labeled based on the concept, it's very similar to the contextual guess and slip model, the probability a student didn't know a skill but then learns it by doing the current problem, given their performance on the next 2. We can calculate the probability that they didn't know it and they learned it from those next 2 actions with an application of Bayes' theorem. So we say the probability they didn't know it and learned it, given the next 2 actions, is the probability of those next 2 actions, given that they didn't know it and they learned it, times the probability that, in general, regardless of those 2 actions, they didn't know it and they learned it, over the probability of those next 2 actions across all contexts. The probability that they didn't know it and they learned it is computed with the standard BKT building blocks, the probability that they didn't know it at the current time, and the probability they learned it. The probability of the next 2 actions is a function of the only 3 relevant scenarios. Either they already knew it, or they didn't know it and then they learned it, or they didn't know it and then they didn't learn it, and their contingent probabilities. So in other words, the probability of the next 2 actions is the probability of the next 2 actions given that they know it, times the probability they knew it, plus the probability of the next 2 actions given that they didn't know it and they learned it, times the probability that they didn't know it and they learned it, plus the probability of the next 2 actions given that they didn't know it and they didn't learn it, times the probability that they didn't know it and they didn't learn it. Or in other words, there are 3 cases, and we're going to take the probability of the next 2 actions given each of those 3 cases, times the probability of each of those 3 cases. One quick example. What about the probability of the next 2 actions given that they knew it times the probability that they knew it? Well, there's only 4 possibilities for those 2 actions. Correct, 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 not correct, not correct, correct, and not correct, not correct. And those turn out to be, if you knew it, the probability of correct, correct, if you knew it, is the probability you didn't slip times the probability you didn't slip. The probability that you got it wrong and then right, if you knew it, was the probability you didn't slip times the probability you slipped, and so on. Now, of course, this case is going to be more complicated for the case that you didn't know it and you didn't learn it, because in that case, we're actually going to try to estimate the probability as we go forward based on the possibility that you may have learned it or not between the first and second attempt. So the equations get really hairy at this point. I'll refer you to the paper for that. Now, P of j, like contextual P of s and g, we took features distilled from logs of student interactions with tutor software that broadly capture behaviors indicative of learning. These features were selected from the same initial set of features previously used in detectors of gaming the system, off-task behavior, and carelessness, aka probability of contextual slip that we just talked about a minute ago. All the features in the original work used only first response data. Later extensions to include subsequent responses only increased the model correlation very slightly, not statistically significantly. And then we had a model that we could use for a few things. Now, this model we're not using at any point to try to improve our prediction of student performance in the system. Instead, we're looking at how we can use this in analysis. It turns out that patterns in P of j over time can be used to predict whether a student will be prepared for future learning. That is to say, when they encounter the first piece of curriculum material beyond the current system, can they actually learn from it and do well on a test? Patterns of P of j during the use of the system turn out to be predictive of this. Also, it turns out that P of j over time can be used to predict standardized exam scores. And in a third recent use, P of j can be used as a proxy for eureka moments in cognitive science research. We can look for moments where students had spectacularly high learning, say higher than 99% of all learning episodes, and say, what distinguishes the behavior that precedes this? There is, by the way, an alternate method for calculating P of j. In that method, unlike the Baker, Goldstein, and Heffernan method, we assume at most one moment of learning, and then we try to infer when that single moment occurred across the entire sequence of student behavior. This was done both by Van de Sande and by Pardos and Udelson. There's some good theoretical reasons why you might want to do this. It actually more closely matches the assumptions of BKT. Is it better? We don't know yet. Although there have been a couple papers on it, we haven't yet seen anyone study whether this approach has the same predictive power as the method from Baker, Goldstein, and Heffernan for things like predicting preparation for future learning, standardizing exam scores, or eureka moments. Personally, I'd really like to see that happen because I think it would really answer what's the best method for doing this.
Finally today, we'll discuss a fourth type of modifying the assumptions of BKT, which is modeling transfer between skills. Unlike the other three, which were kind of looking still within a skill, essentially, even though some of the variance in contextual guess and slip varied by skill, this one actually says, what if we relax the assumption that each skill is independent from every other skill? A first paper on this comes from Seo Pedro and colleagues in 2014, and what this model did was it said, all right, classic BKT said that there's going to be a separate BKT model for each skill. BKT PST, partial skill transfer, says instead that each skill's models can transfer in information from other skills. And in its original formulation in 2014, this happens exactly one time when switching between skills in a system. But Kang et al. In 2022 said, wait a minute, sometimes you switch back and forth between skills. So in that case, we're going to do it at each time step. The BKT PST or PSTC model basically is the original BKT graph, which you see at the bottom, but then from some other skill, there's a transfer in which has parameter k. This method of transferring information between skills hasn't been used a ton, but it has been used by Seo Pedro and colleagues to study the relationship between skills in a science simulation. Specifically, if you master skill A, are you starting off better in skill B? Kang and her colleagues used it to study which research skills help graduate students learn other research skills across several years. In that case, every year the grad student might be getting better in each of several research skills, and the question is, if they acquire skill A in year N, are they better at skill B in year N+1? So overall, across all four of these types of examples, contextualization approaches generally don't appear to lead to big overall improvements on predicting within tutor performance. But see Gonzalez, Brenes et al. 2014, but in general. But what they're really good for is other purposes. Things like predicting robust learning, understanding learning better, and understanding the relationship between the skills. There's a lot of utilities to modifying the assumptions of BKT that are harder with some of the more contemporary algorithms, which is one of the reasons why researchers still sometimes use BKT. That concludes our discussion on contextualization of BKT. In our next lecture, we're going to talk about the algorithm that everybody's talking about, DKT, deep knowledge tracing. Thank you very much. See you next time.